So let us solve some questions from GATE. Here there are 4 polynomials. We need to check what will be the dimension of the space generated by those 4 polynomials. So if we write the coefficients, if we take this as a basis, t square t and 1, with respect to this basis, the coefficient of t square plus t plus 2, it will be, if we write the coefficient, it will be 1, 1 and 2. So all the coefficient, if we write all the coefficients in a single matrix, that is coordinate vectors, it will be 1, 1, 2. Then for this will be 1, 2, 5. Next will be 5, 3, 4. And the last one will be 2, 2, 4. Now if we use the row reduction, R2 minus R1, to remove this thing, and to remove the entry 2, if we subtract 2 times the first row, then first row will be 1, 1, 5, 2, same thing. And now row 2 minus row 1, this will give 0, 1, minus 2, 0. R3 minus 2 times this row, this will give 0 here. 5 minus 2, that is 3. 4 minus 8, minus 4. And after that 4 minus 4, that is 0. 4 minus 10, sorry, this 4 minus 10, this will be, actually this is minus 6. Now R3 minus 3 times the second row, this will remove the entries from the third row, and they have the same 1, 1, 5, 2, 0, 1, minus 2, 0. So from here we are getting a upper triangular matrix, and clearly this reduced matrix R has rank 2. Therefore from those 4 vectors, only 2 vectors are linearly independent, since the rank is 2. Hence we can say the conclusion is dimension of the vector space W generated by those 4 vectors actually 2. Let us solve the next question. Here the time, and there is only single relation. Okay, so the guess will be the total dimension should be R5. R5, since it is R5, the dimension of this space is 5, generated by those vectors E1, which is 1 and everything is 0, E2 is 0, 1 and 0, and similarly up to E5, dimension V is 5, generated by those 5 vectors. But here we can see there is a single relation. Hence we can express x2, here we can express x2 as minus 3x1 minus x3. That is, any vector x1, x2, x3, x4 up to x5, this can be written as x1 minus 3x1 minus x3, then x3, x4, x5. So it is same as x1 times 1 minus 3, 0, 0, 0, plus x3 times 0 minus 1, 0, 0, 0, and similarly x4 times, sorry, there will be another one because coefficient of x3 is 1 here, and those are the second entry, which x4 times 0, 0, 0, 1, 0, plus x5 times 0 everywhere, except the last entry. So we can see that the vector space actually generated by those entries. If we denote it by alpha 1, alpha 2, alpha 3, alpha 4, so the subspace W is generated by alpha 1, alpha 2, alpha 3 up to alpha 4. And clearly those 4 vectors are linearly independent, because if we write those vectors in rows, that is 1 minus 3 and everything is 0, then the second row is 0 minus 1 1, everything is 0, then it can be seen that. Let us check this. So if we put those entries in a single row, it will be 1 minus 3 0 0 0, 0 minus 1 1 0 0, here 0 0 0 1 0 0 0 0 0 1. So we can see that all those rows are independent. Okay, if we reduce, we can remove these. We can apply row reduction, then R2. So we don't need row reduction. Actually, this is already reduced. It is in. So here we can say that those rows are in linearly independent, because if we see these entry, those each rows contain the pivot entry, right? Therefore, the rank of this matrix is 4. Hence, alpha 1 up to alpha 4 are linearly independent, which generates the vector space W. Therefore, basis and dimension of W will be 4, and the basis is given by this. Hence, size this. Let us solve this question. Here, if we write in matrix form, the equations can be written as 1 1 1, 1 minus 1 minus 1, then 1 minus 5k times xyz equal to 346, right? So if this coefficient a is invertible, then ax equal to b, this should have solution x equal to a inverse b. So this is unique solution. But if a is non-invertible, then the system should have infinitely many solutions, right? So we need to find the value k for which a is not invertible. Okay, so a is not invertible if and only if determinant is 0, and determinant, let us find the determinant 1 1 1. This is same as, let us use this operation R2 minus R1 and R3 minus R1 to find the determinant easily. Then it will be 0 minus 2 minus 2, and similarly 0, and here it is minus 6, and then it is k minus 1. So it will be same as, if we expand the determinant with respect to this column, first column, then it will be 1 times minus 2 minus 2 minus 6 k minus 1, which is same as minus 2 times k minus 1 plus 6, right? K minus 1 plus 6, that is k plus 5. So this determinant is 0 if and only if k equal to minus 5. Therefore, this is the answer. Let us solve another question. Here it is from GATE 2007. A is given by this matrix, and the vector space are xyz from R3, that is subspace of R3, such that those xyz entry satisfies this relation. Clearly, xyz this determines 0. This means this R3, the third row, this is actually linear combination of the first row, okay, A1 times this plus A2 times the second row, 2 to 3. And we know, we can easily see that those two vectors are independent, linearly independent. Okay, therefore xyz are, those xyz are generated by linear combination of those two vectors. That is, xyz belongs to span of this, if we denote it by alpha 1 and alpha 2, span of alpha 1 comma alpha 2. And alpha 1 and alpha 2 are linearly independent. So clearly you can see the dimension is 2, because the basis is given by this alpha 1 alpha 2. Why those are linearly independent? Again, put it in rows, 1 1 1 2 2 3. Then if we apply row reduction, this will reduce to 1 1 1 0 0 1. Again, each row contains pivot, so there are two non-zero rows, so rank will be 2. So this is the answer. Next, let us consider this question. Here